$1,000 camera.
Everything's fine?
So today is the third lecture, right?
Yeah.
So do we have the PPT from the previous two? So we shared among ourselves.
I have both.
And after two lectures, we already see great impact, especially Haiyan and Beeman's work.
I hope so.
Very promising. And we'll have the next 4 months together. Imagine how much we can do.
We can do a lot.
We can do a lot.
They're very good.
Okay. And Biden and Jing will catch up. They will catch up. Yeah.
They will.
So thank you for introducing the concept of flatness to us, and we will enjoy the lecture tremendously.
Thank you. Thank you very much.
Yeah.
You're very kind. It is my hope that this idea of flatness becomes usable for people who are not aware of the big potential of this technique in controlling linear, non-linear systems, continuous time systems, discrete time systems, even infinite dimensional systems. So in a sense, this is an all-prevailing technique which enjoys the property of being ubiquitous, in the sense that it can be applied anywhere. So let's explore discrete time systems, and just to begin, we will start with linear time-invariant systems. That class of systems is particularly useful because many man-made systems are of that sort, and many important models of social behavior, like economic models and so on, can be approached from this viewpoint of having discrete values of time and looking at the evolution of a system at certain instance. So the concept of flatness there would be, to start out with for the case of linear time-invariant systems, that you will have a privileged variable that you can identify within the system, either by inspection or by applying a formula that we will present in these slides, which has to do with everybody else. I mean, it's a variable that has the property of being able to parameterize in a difference manner rather than a differential manner, as we were talking about in continuous systems. It has the virtue that it can parameterize all system variables in terms of that particular variable and a number of, let's say, forward time shifts or advances of that variable. We will call that a difference parameterization. And what we look for is to establish the relations between the states, the inputs, and the particular output of the system in terms of this unique variable that can express in forward time shifts the particular value of each of the states. So we will start then by assuming that our discrete time system is being described by a transfer function in the z domain. The z domain is the variable that is commonly used to express forward time shift. So the output satisfies a relation with the input through a certain transfer function, which is a rational function of z. And this rational function doesn't have to be proper. It might have a numerator which is of order larger than the denominator, as we will see in many examples. Many of the properties of continuous time systems don't have a counterpart in discrete time. There are different descriptions. And therefore, transfer functions in the C domain, which is the Laplace transform of shifts in time, we say that this system is controllable if and only if the polynomials n and d are coprime. In this case, the definition of flatness coincides in a spirit with the definition of flatness in continuous time systems. So if you have a transfer function characterized by a rational transfer function that is the quotient of two polynomials in C, then if those two polynomials have no non-trivial common factors, then the system is said to be controllable. And that's the definition of controllability. So let's put an example to see how this can be quickly applied to a very simple model of a gambler, and to explain why gamblers usually ruin themselves by playing. You have two players, the gambler and the house, for instance, and during any draw of the game that they're playing, there's a probability that the gambler takes one win, and in this case it will be represented by taking one chip or a coin or a bill from the house, and a probability 1 minus q that the house takes the chip. So it's two players really, the gambler and the house. Each one has a probability, and these two probabilities are complementary in the sense that they're normalized. If you add q plus p, you would get 1. So assume that the gambler starts with A chips and B starts with B chips, so that at some moment between 0 and the total number of chips, which represents the possibility of adding 1 at that time k or subtracting 1, let's say A has A plus B, and B has A plus B minus K. So for any K between between 0 and A plus B. So the probability that A eventually wins is denoted by U, and the probability that the house wins it will be 1 minus U. So the player with all the chips, when he wins all the chips, when one of the players has all the chips, the game stopped. So we have the following model. If we call U the total number of chips in the following draft, there is a probability of value p that a probability of value uk plus 1 with certain constant that the gambler will have k plus 1 chips, and a probability q that it will have k minus 1 chips. Let's suppose the house can intervene with some control action in this dynamics, and we will start with the number of chips being 0, and the total number of chips at the end it will be 1. Some one of them has to win at the end. So the V is a secret tampering of the game, acting as a control input, and it's chosen each time as a small number, let's say between 0 and 1. So for that particular model, it's very easy to get the dynamics, and the dynamics the input-output dynamics, in which V is the control applied by the house, will produce this result as this weighted sum of the probabilities and the number of chips in each draw and the following one. When you take C Laplace transforms of this model, you will get this input-output relation. So now you see that the system is totally controllable from the house. So that means it can move the state wherever the house wants. And this is why the houses try to be fair, because if they can interfere a little bit, it makes the whole game controllable by the house, and surely the gambler will be ruined. And this is a consequence of controllability in discrete time systems. So that's one little lesson there, that one shouldn't go to houses which are not highly dependable and honest. So a linear system described by that transfer function will be flat if and only if the system is controllable. And what flatness means here is the possibility of parametrizing inputs and outputs in terms of this flat output and time shifts, forward time shifts or advances of the flat output in a finite number. So let's assume that the system is controllable, then we can define, if we have a numerator n and a denominator d, and our input-output relation is like this. Let me call this y of c and u of c. So if we, again, as we did in continuous time case, if we define x as u divided by d, then evidently the output y can be written as n times x. So x is a particular variable which can define the inputs and the outputs in terms of advances. In terms of advances of the flat output, and the control can be also expressed as a difference function of the flat output. So undoubtedly this is a representation of the dynamics of the flat output, and x itself will be the flat output. So that is pretty much the same of what we had in continuous time. And because these two polynomials are coprime, they don't have common factors except possibly one, the number 1, or a constant factor that just vanishes from the division. Then the Bezout identity has to be satisfied for those two polynomials, in the sense that there exists a pair of polynomials a and b such that this product is equal to 1. This sum and product is equal to 1. So that means coprimeness is exactly the same, and Bezout identity is the same homologous one to the one we have in continuous time. So if we multiply the Bezout identity, which is equivalent to the coprimeness of n and d, multiplying this out by c and using these relations, we get that the flat output is an endogenous function of the input and the output of the system in terms of forward shifts in a finite number for y and for u. So in that sense, the flat output is an endogenous variable that only requires inputs and outputs to be defined, and a finite number of advances of those inputs and outputs. So everything here up to this point is equal to what we had in the continuous time. All we have to watch out from now on is to make sure that this definition does not contradict the restriction of causality. Causality is the name of the game in discrete time systems. It's very easy to make mistakes in discrete time systems and take the equations and suddenly realize that these equations cannot be implemented in real life because you need information from the future in order to describe the present, and that's not physically possible. So the variable is endogenous, and it difference parameterizes the outputs and the inputs of the system. And this is the same as in continuous time system. And in that particular transfer function representation, then we have complete characterization of flatness. And to see the reverse implication, if the system is not non-controllable, it cannot be flat, then assume that n and d are not coprime. That means they will have a common factor, which is non-trivial, and that's called the common factor f of c. So actually, the numerator and the denominator will have a factor f of c affecting certain polynomial in n0, which is part of the numerator, or certain polynomial d0, which is part of the denominator. Since the system description is something like this, n of c times u plus d of c times equals I'm sorry. D of C times Y minus N of C times U equals 0. This should characterize the same as this, the description of the system. But if there is a common factor F between the denominator and the denominator, we can pull it out as a common factor and get here, let's say, D0 of C times Y minus N0 of C times U. And this could be very well the product of that factor times a certain variable C such that this is 0. If F acts on a certain variable and produces 0 as the result of a dynamics that is not present in the system, is a hidden dynamics that might be present there, this would be true. So this function acts as a hidden dynamics. It has something inside which is not here, and that thing which is inside the system, which is not visible from the representation, is a certain variable that satisfies that when you apply this polynomial to that variable, you get 0. That means that C evolves only on the basis of the initial conditions, and therefore C cannot be controlled. So there is some hidden part of the dynamics which is uncontrollable. So if the system is not controllable, it cannot be flat. It cannot be flat. So this is the if and only if final consequence. If the system is controllable, and the polynomial representation in transfer function form has numerator and denominator which are coprime, then that means the system is flat. And if the system is flat, it is controllable. So this is just the characterization of controllability. Let us take an example, the temperature control of a tank, in which you have this description. This is a controllable model because you see the transfer function representation. This is the output temperature, this is the input temperature, and this represents the dynamics of how this temperature is varying from the input towards the output. And of course, because the numerator and the denominator are coprime, they don't have any common factors, this system should be controllable. And of course, according to this recipe, the characterization of the flat output can be made in terms of the input by means of this quotient. This input divided by this operator will be the representation of the flat output. So we can obtain the representation of T, so the input temperature or the output temperature in terms of that flat output F. So for instance, the input temperature will be the flat output times this polynomial. So and the output temperature will be the flat output times this polynomial. So we have a complete difference parametrization of the input and the output in terms of time shifts of the flat output. So those relations in the time domain simply mean that the input temperature is this function of the flat output taking into account forward time shifts of the flat output of order 2 and 3, and a linear combination of those two forward time shifts gives you the input. And the output will be also a combination of time forward shifts for the flat output.
Do you have a causality problem there?
Yeah, then of course you immediately will say, okay, but can this be useful for implementation? At this point, since we're not solving any control problem, I would say if I have a trajectory for the flat output, this relation, and I have this trajectory that I know at this very moment, and I know what the values are going to be in the future, but I have it now. I say I want to follow this trajectory step by step, going from, let's say, one equilibrium to another, and I would like to do this in 7 time shifts. There is no problem in knowing all the values that you will be needing in the future for that trajectory. So if you know a trajectory for the flat output, you will not be able to know the nominal values of the input temperature and the output temperature, because they are parameterized in these terms. Moreover, you can also do some analysis of the equilibrium. So this representation, even though it's telling you the value of the control input on the basis of future values of the flat output, at least is useful for analysis. The question of controlling the system is still a different question, and we have to watch out.
Same equation can be written in a backward shift.
Yeah.
Would that avoid the causality problem?
We will get to that, yes, yes, of course. For instance, if you define the flat output as the first state, and the forward time shift of the flat output is the second state, and the second forward time shift as the third state, and the control is just the control input of this input-output model, and y is representing the output, then evidently the forward shift of the first state variable, fk plus 1, will be the second state variable. The forward shift of the second state variable, which will be fk plus 2, will be the third variable, and the controlling and the third shift of the first output, which is the first shift of x3, will be related to u. And the output will be a linear combination of x1 and x2, as we saw in the previous slide. So we have a traditional linear time-invariant model for our system, and this, of course, is a state representation, traditional state representation, that can be put in the C domain very easily by replacing each one of these left-hand side terms by C multiplied by x1, or C multiplied by x2, or C multiplied by x3. And as a representation is a traditional, very nice representation, only that there is a non-causality hidden here, because we will see that in the difference parameterization and the definition of the input-output relation, the flat output will be defined as a forward time shift of the variable x1, which is not available in the present. So, but as I said before, the equilibrium conditions can be studied from this. If you have a given equilibrium for the flat output, that will produce a given equilibrium for the input and a given equilibrium for the output temperature. So it's a way of parameterizing where are you starting and where can you go in terms of shift or motions of the system from equilibria to equilibria. One initial equilibria will be forced to move to another equilibria. In terms of this parameterization, I can pre-compute where are things ending, or what should I do with the equilibrium of the output? What do I need here in order to obtain certain values of the output temperature?
What's the flat output in here?
Okay, the flat output, we haven't computed it yet, but the representation of the dynamics of the flat output in terms of the input is this, only that it will be a function of the inputs and the outputs, and we will do that in the next slide. So because of Besut identity, you have the numerator and the denominator, then there must exist, because the system is controllable, you have two polynomials that can be multiplied by the numerator and the denominator and obtain 1. And we postulate that the first polynomial is quadratic in C, and the second polynomial is constant, excuse me, and the second polynomial is constant. Then we will have the possibilities of solving for the coefficients of these polynomials A and B. And when you do that, you obtain a set of equations for the coefficients M, N, P, and B. So it's 4 unknowns and 4 equations when you equate all the respective powers of z to 0, except the last one equals to 1, you will have the possibility of solving for the polynomials a and b, the coefficients of the polynomials a and b, and you will have that the flat output is represented by a polynomial in C affecting the output and a constant polynomial affecting the input. So the flat output is a function of the input and the output. But as you can see, the flat output is defined in terms of forward shifts of the output and the input. And those forward shifts are shown here in this representation. That means that in order to define the flat output in the present, you need the values of the output in the future. So intrinsically, you have here a lack of causality. You know what the flat output expression is, but if you want to compute it in the present in terms of actual signals, you would need to explore the future. But on the other hand, if you want an evolution for the output temperature, you can do a lot of things with this knowledge, because you can pre-compute also many things like the flat output and inputs and outputs that are needed in order to obtain certain motion. So it's not a complete waste of time to have this parametrization. Naturally, everything would be offline. When you want to get your hands into implementing what this solution is telling you, of course, you have to go to a causal representation of your system. And the causal representation utilizes the backward time shift. So the input temperature the input temperature and the output temperature related by this transfer function in the C domain is also equivalent to this one containing negative powers of C. Since the system is third order, we have here multiplied by C minus 3 the numerator and C minus 3 the denominator. That means we have taken the system variables and we have shifted them back to the past at least 3 times or 3 steps. And when you have that, and you can still define the flat output, because these are now polynomials in C minus 1, and these polynomials are coprime, and the system should be controllable, or it is controllable, and the representation of the flat output can be made in terms of the transfer function in terms of C minus 1. So F and the input are related by these dynamics, and now that the dynamics of F relies on past values of itself and the actual value of the control input.
The denominator, is that Z minus 1 or Z minus 3?
C minus 1. Because you multiply everything by C minus 3, yeah, and this C square gets here too. So, so the flat output satisfies these dynamics, and the output of the system can be represented by means of these backward shifts in terms of the flat output, which is this quotient. So you'll have the value of the flat output at time k minus 2 and the value of the flat output at time k minus 3, defining your actual output temperature. So this representation is now causal. In the sense, your output temperature only requires information from the past in terms of the flat output. And the flat output can be computed recursively in terms of information which is also either in the present or the past. But it doesn't require anything in the future. But now the thing is, we can redefine now the state space representation of those relations by defining the first state as the most backward shifted value of the flat output, and the second state as an advance of that, or a forward shift of the previous one, and a forward shift of this will define the third state, and the control and the output will be defined in the same manner as before. So when you do this, you get exactly the same state representation. It's not different. It's the same, exactly the same that you had before in the non-causal way, but now everything is causal. And it's only that the interpretation is that you have taken your system variables, which are represented in a non-causal way, and you set the thing backwards in time until it became a causal representation, and it doesn't require values from the future in order to be defined, any of its variables. And now you take the time origin and you put it at the beginning, and you have exactly the same representation. And now you can do things with this. So the lesson here is that the state space representation is invariant, in a sense, from the viewpoint of flatness, whether the flatness variable is non-causal, the flatness variable is causal, whether it depends on the future, it depends on the past. The state space representation will be the same. So you can use this in order to, you can use the traditional representation in order to do design. All you have to take care is that these states are defined now this way. So trajectory planning and all tracking trajectories and things like that have to take into account that the states are now shifted back from the previous representation a sufficient number of times so as to avoid the necessity of having information from the future. And this is the representation of the system. So that makes things very simple, because the analysis we had from the equilibrium and all that is still valid here, is equally as valid because the state representation is the same. So the equilibrium relations between the initial value of the flat output and the final value of the flat output in terms, let's say, of the output temperature is a one-to-one relation in which you say, I want this equilibrium value for the output temperature in steady state. This will have to be the initial value of the flat output, and this will have to be the final value of the flat output. Now that you have initial values and final values, then all you need to have is a trajectory which interpolates between those two. So at time, let's say at time ti, you have this, and at time tf, which is, you know, in a discrete fashion is an integer number of samples, you have an initial value of the flat output, which is motivated by your desired initial value of the output temperature, and a final value of the flat output in steady state, which is motivated by a desired final temperature of the output, and you place a trajectory that will sort of do a smooth transition between an initial value and a final value. Or you can have any trajectory you deem necessary to produce. That is very simple to estimate or to specify in terms of Bézier polynomials. And those polynomials will give you a very nice smooth rise or descent of the desired trajectory in terms of a finite polynomial in the variable c. So the trajectory can be planned to depart from this initial flat output and land at this final flat output in terms of the initial equilibrium value of the temperature and the final value, desired final value of the output temperature.
What if the initial value doesn't meet the requirement, the initial flat output?
Well, this is only trajectory planning. The control, we haven't defined a control yet. Right. So this is only planning what we want to do. Yeah, whether we can achieve that, because the system is controllable, you will always be able to follow trajectories.
You can control the flat output to the final value. But can you control the initial value of flat output?
Well, the initial value is given by nature.
Right, but in here you have conditions.
Oh no, this is the trajectory. This is not the response of the system. This is the trajectory you want to follow.
So you want the initial output, flat output to follow?
Yeah, you say, okay, I have a process in which my temperature is in steady state, everything is in equilibrium. Now I want to move that equilibrium to another value. So my initial value should be that equilibrium. And you want to move to another equilibrium which is different. Now you have a trajectory that you desire to follow. Okay. But possibly you didn't measure things right, and your initial value of the temperature was not aligned with the trajectory. Right. So well, you have to control it. We haven't talked about control now. We are only talking about planning the trajectory. And then we will try to control that, to make that tracking error go to 0. That's what we want to do. So for this, we can specify this trajectory. This is a nominal trajectory that we would like to follow in terms of a Bézier polynomial. And here is a very simple example in which you have a polynomial, let's say, of order 7, in which as time goes on, it takes when k is equal to the initial value k0, everything is 0, and when k is equal to the final value capital K, you will have a 1 here, and this sum will also add up to 1. So this polynomial is smoothly interpolating between 0 and 1. And if you have that, then you can do anything with that particular trajectory to make a polynomial that goes from an initial value which is arbitrary to another final value which is also arbitrary. And the way to do that is to make up this sum. The desired initial value plus the difference of the final value minus the initial value multiplied by this polynomial which varies between 0 and 1 in a time interval that goes from k0 to k. This will give you a trajectory that's smoothly interpolating between fi and ff. But the basic thing is to specify this polynomial that interpolates between 0 and 1. And when you have that, this combination will give you the desired effect. Because the desired trajectory can be constant before the initial value of time, can be constant after the motion of the system has ended, and it has the intermediate value which guarantees this smooth transition from one equilibrium to another. So when this function phi is equal to 0 at the beginning, the value of f star is just the initial value. When this function is 1, fi gets cancelled and ff is imposed. So this is a nice way to track a trajectory which gives you a change of equilibrium. This is all based on the flat output, and there is no control design yet. It's only trajectory planning in terms of the flat output, because the flat output parameterizes the output of the system, and in particular it parameterizes the equilibrium of the output. So if you want to move the equilibrium of the output of your heating system from one value to another, this would be the way to planify the trajectory that you want to track. Now the control problem is, how do I guarantee that the actual motion of the system comes to coincide with that trajectory and follow it without deviations? Of course, if there are perturbations, then there's more things that you should take into account in order to make the system robust with respect to disturbances that can be endogenous or exogenous. But that's part of another problem. So initially, this completes the trajectory planning. Flatness allows you to do trajectory planning in terms of conditions that you want to obtain from any particular variable of the system. Let it be called the output or one of the states that you're interested in controlling. Because of the parametrization, you can always set the motion to be whatever you need in order to make either the output or one of the states behave as you want. And of course, you will have a reflection of that planning on your input. This planning will also affect or describe what is the nominal input that you will need. And if this nominal input is exceeding some magnitude value that you don't want to exceed because your actuator doesn't allow you to do so, then this planning can be modified in order to make the input satisfy certain constraints, like magnitude constraints, or velocity constraints, or any other kind of constraints. So flatness allows you to preview the system and its properties as reflected in the desired motion that you want to impose, and respect still certain limitations of the system. This is one of the things that the flat output will always provide you, whether in continuous time or discrete time. So what is the controller? Well, the controller is a simple tracking controller in which you're trying to cancel the internal dynamics. Remember that the flat output has this dynamics. This is the dynamics of the flat. That's what you want to control. You have an initial value of f, you have a final value of f. This is your actual control input to the system, and this is the dynamics that is being satisfied by the flat output and its relation with the input. So remember, the system is third order. Nevertheless, the dynamics of the flat output is first order. This is something that happens in discrete time systems. In continuous time systems, you have a perfect matching of the orders of the flat output differential equation in relation with the input. That equals to the dimension of the state. Here, the situation might not be that. But it doesn't matter, because you are always able of producing a third order equation out of this dynamics, in the sense that first of all, you'll try to cancel this. Let's say you cancel this and you impose a second order polynomial in backwards shift time, time shifts, that reproduces a third order dynamics for f, which has nice properties, like it goes to zero in a potential way. So it goes to zero step by step. So since this is the dynamics, this is what we want to control. So specify the control input so that f satisfies certain dynamics. And the dynamics of f, of course, is going to be a stable dynamics for the tracking error. So u will first have a precompensation of the nominal flat output, and that will subtract from the actual flat output at time k plus 1, and that, or at time k, and that will produce the error at time k, the tracking error at time k, when you use this first term in your controller. Then you're adding a linear combination by means of these coefficients k3, k2, k1. You're adding the error of the backward shifted flat output 1 unit of time and 2 units of time. So you are creating a third order system. You're canceling the dynamics of the flat output in the first term, and you're adding all these tracking errors successively in time, the tracking error of the previous instant of time, 2 instants of times, and 3 instants of times before. So you're doing causally, you're taking a linear combination of the tracking errors in time, canceling the dynamics of the flat output, and precompensating with the nominal value of the flat output. This is the traditional way to do trajectory tracking. So when you do that, you can put everything back in terms of the state, and using the states of the system in the state space representation that you have defined previously, and the nominal value of the control, because of the input to flat output relation, is just this. So everything is known here, and you have a nice polynomial in the tracking error that this dynamics causes when you close the loop in the system. And when you close the loop in the system, the tracking error is seen to satisfy this backwards shift relation in which you have causality describing the behavior of the tracking error. And if you choose the coefficients k3, k2, k1, so that the Laplace transform of this in terms of c minus 1, and then you put it in terms of c by multiplying by the appropriate factor of c, you want that polynomial in C to have all the roots in the unit circle. And when you do that, what you're doing actually is you're controlling your tracking error by means of a difference equation in which all the coefficients are assignable and having stability towards 0 of the tracking error. If the tracking error is going to 0, then the flat output is going to the desired trajectory, and the control goes to the nominal trajectory, and everything is as you planned for. So this is linear control. This is a nice linear controller, and this is the result of the simulations. You specified in red the desired value of the flat output for all times, and you started off the initial condition a little bit off of the desired initial value, because that might be the case in real life. You thought that you were going to achieve this equilibrium, and you found yourself at a slightly different equilibrium, and you want to control that to make the the flat output track this trajectory, because that makes your output track the desired trajectory and go from the initial to final desired equilibrium of the output of the system, and the input will have a nice behavior that you deem it was possible because it didn't infringe any of your limitations in the control magnitude. So tracking the flat output desired trajectory gives you the desired output trajectory for the temperature of the system, and gives you the profile that you need to apply online in a feedback manner to your system in a planning that takes probably starts, let's say, at 4 and ends up at time t8. So in 4 clock pulses, your system will react, and you will go from the initial equilibrium temperature to a final equilibrium temperature. And this is how it's done. Any question?
So the controller is third order, the flat output is first order, but system is third order. So the order of controller is determined by the order of the system.
Yeah, but in discrete time systems, it's not like that.
But in your case...
Oh, you force that in order to have a complete design.
So if your controller is, say, second order, then you would your closed-loop error equation would not be completely specified.
Yeah, you might try to influence F by means of these dynamics,
Right.
And but remember, for instance, the output temperature it depends on values of the flat output which are not in that time domain. In fact, it's 2 and 3 steps before, so you quickly manage to drive this to F, but then the output temperature will have to wait a certain number of steps before it starts reacting, and that is not. So you have an implicit delay there that you don't want to deal with. You want things to start right on time, and that's why you impose a third order dynamics, because that's compatible with the system. Otherwise you have a sort of zero dynamics in the beginning, just waiting for the system to react, because the output variable is way back, and you already influenced the flat output, and the output started to move later. And that's not good, because if in the meantime you have perturbations, you won't be able to control them anymore. So you want to have a match of the flat output dynamics with the order of the system, even though the natural relation with the input is not of the desired order, is not of the required order. Yes, that is a valid observation. How about the non-minimum phase issue? Well, it's very much the same as in continuous time. Let's suppose you have a transfer function of this form, where the value of A in magnitude is larger than 1. So this is an unstable zero dynamics. And you have a stable denominator, because the root of that denominator is going to be in minus B, and the absolute value of B is within the unit circle. So you have a nice stable system, but with an unstable zero dynamics. So the way flatness gets rid of that problem is that you see the state space representation of this system will tell you that if you call this X, then xk plus 1 equals to minus bxk plus u. This gives you the dynamics of a flat output X, which is represented by this quotient. And the output Y is just that applied on the flat output, but since the flat output has some dynamics, when you compute y, you will have this representation in terms of the flat output and the input. So this is a system in which you want to control things. You want to control the output. For instance, it's very easy to see that if you put UK, you cancel these dynamics, then you drive to 0 in just one step. But then you have a zero dynamics, and the zero dynamics reflected here will be that since you are using this control, you would be canceling the stable pole and imposing an unstable 0 in the flat output dynamics. So don't be deceived by the fact that the flatness gives you the nice relations, because if you take this approach, the 0 dynamics that you will obtain is unstable. So that's not the way to do it. And for instance, one example of that is this river model, which clearly has a 0 in the numerator, which is the quotient of this number divided by this number, which is smaller than that. So the root of this polynomial is beyond +1. And therefore the system is non-minimum phase. It has an unstable 0. And the polynomial in the denominator is given in this case by this representation. So the 0 dynamics is clearly unstable. That's dynamic which is always bothering you in real life. So in order to move around it and to be able to to come up with a design that doesn't give you that internal unobservable instability of the system, once your output is stabilized, things start blowing up, and you don't want that internally in the system. So we take the flat output approach. We compute the polynomial, the Besut polynomial coefficients a and b, a multiplied by this numerator and b multiplied by the denominator should be equal to 1. You can compute the coefficients of a and b, and it turns out that b is first order and a is second order. Incidentally, there are many computer programs that do that for you automatically in your preferred computer simulation package. So the system is controllable clearly because this is coprime, this numerator is coprime with the denominator, and there's no common factors. Therefore, the flat output is defined as a relation of the inputs and the outputs. So there is an endogenous variable, which is the flat output. And now we will not care anymore about the possibilities of becoming non-causal, because we know how to define the state in order to obtain always a causal representation. It will be the same discrete time system in forward time representation as the state equations are normally represented, but we know that everything we're doing is being planned in a causal manner. So the output of the system has this dependence on the flat output, and the input of the system has this dependence on the flat output. And remember that because we have two time shifts forward into the future, it doesn't mean that this is not available. This will be available because our definition of the flat output will be such that we can do that. So the state representation of the system in traditional terms will be that of a linear system with an A matrix and a B matrix, and the actual output being a representation in terms of the states naturally associated with the flat output. So the problem is to design a controller that moves your flat output from one initial equilibrium to another final equilibrium, motivated by the desired value of the output. and since everything is parameterized and is explicit parameterization, then you can study your equilibria, see what the initial value of the output is, what the final value of the output is you want it to be, what should be the flat output doing in that interim between the initial value of time until the final value of time. So it's very much the same. And of course, because of the flatness representation, the flat output representation in terms of the input, this polynomial happens to be stable, and therefore the flat output will be stably controlled by U delta. Moreover, if you have some instability here, you can eliminate it from the input. So in essence, the flat output is going to be controllable, and you can track any trajectory, and somehow the no minimum phase problem vanishes in the air, because you're not controlling an unstable system, you're controlling a stable flat output dynamics. And that reflects on the value of the outputs, and there is no instability there, because it's a mapping which, when you have the flat output, you immediately can compute, let's say, the output of the system, or the input of the system, or any state of the system, and therefore there is no conflict of having zero dynamics. Remember, the flat output does not have any zero dynamics. So whatever you do with the flat output is final. There is nothing internally cooking up that will destroy your stability. And that's one of the advantages of flatness. In general, if you have a linear system in the state space, which we assume is n-dimensional, this is the traditional representation of a time-invariant linear system coming from an input-output representation as a particular realization. And this system is known to be controllable if and only if the Kalman controllability matrix is non-singular. And the way to build that matrix is to take the vector B and the matrix A and conform this composite array of vectors B, A, B, A squared B, and so on, up to the n-1b. So this is the Kalman controllability matrix. If the rank of this is full, then we say that the system is flat. And if the rank of K is full, we can use K to represent a change of state from X, let's say, to a new state C. And we use this state space coordinate transformation, which incidentally leaves the input-output representation exactly the same, if we had one to start out with. So that's nice, because we work in a state space that is directly related to the controllability of the system, and it will produce a canonical form. So if you have that state coordinate transformation, is a simple exercise to show that you see you have this state's representation, and you produce a new variable C, which is the inverse of the Kalman controllability matrix multiplied by the actual state. So at each moment of time, Ck is K inverse, the inverse of the controllability matrix times X. So evidently from this relation, Ck plus 1 would be the product of Kc inverse times Xk plus 1. But Xk plus 1 is A times Xk, and Xk is Kc times Ck plus Kc inverse Bu K. Okay? So the next state C will affect the state Xk plus 1 through Kc inverse, and therefore you multiply these two terms. So this matrix, let's call it F, satisfies the property that Kc times F is equal to A times Kc. And from this relation, the way to compute F or if you do it row by row, you will realize that knowing A and the controllability matrix, which is B, A, B, and so on, B, A, B. Hamilton theorem, AN can be placed as a linear combination with these coefficients in terms of the previous powers of A, starting from the 0th power up to the power n minus 1. So when you do that carefully, you will see that your transform matrix in the new representation will be something like this. So the state variables naturally here can be written down explicitly from the first one to the last. But you observe that, for instance, the last variable, which is repeated here, allows you to compute Cn of k. So if you know Cn of k, you will be able to compute Cn minus 1. If you know Cn minus 1, you can compute Cn minus 2, and therefore it turns out that you can compute all the states, and you can compute also the control, because the control is just a combination of those states that you know. So what this is telling you is that the last new state is the flat output, in a sense. And therefore, what it means in terms of this representation in K is that a linear system like this, if it is controllable, then the flat output has to be the last state in the new state space representation, and that state is just the last row of the inverse of the controllability matrix multiplied by the state. So the last state here is the last row of the inverse of the controllability matrix multiplied by the state. And therefore, it's the same recipe as for continuous time systems. If you have a representation like that and you compute the Kalman controllability matrix, when you take the inverse of that matrix, the last new state, transformed state, will be the flat output, because that state can parameterize all the states in the system and the input. Therefore, the last row of the controllability, of the inverse of the controllability matrix, will provide the relationship with the original state vector to produce the flat output, which is the last component of the transform variable C. Therefore, we are back in the same kind of formula to determine the flat output of a discrete time linear system, as it was done in the continuous time case. Now, we would like to explore a little bit the issue of discretization in the terms of the delta model, so-called delta model of discrete processes, or exact discretizations, and compare them to see what the structural properties are revealed by the flat output. So consider you have a discrete time system which arises from an Euler discretization with a time interval of value 1. So since the clock evolves in an integer manner from 0, 1, 2, 3, etc., just adopting the integers as the evolution interval, or the evolution line, then the state representation of an Euler discretization, which is an approximation, and if we take t to be the natural step instead of 1, you will have this sort of approximation, in which, let's say, you have x1 dot equals x2, x2 dot equals, let's say, u. This is a simple second order system. That means that if your output is x1, you have a y double dot equals u. So it's a very simple second order equation. When you do the Euler discretization, you approximate x1 dot, you approximate it by this forward difference, x1k plus 1 minus x1k divided by t, where t, let's say, is your sample time. So this is an approximate model of this differential equation, of this linear system. And then we will do an exact discretization, because this being approximate is obtained simply by approximating the derivative in this manner. And the second derivative will also be this value minus the previous one divided again by t. That gives you a t squared in the denominator. And then you can obtain the controllability matrix of this system, with the matrix A being 1t and then 0, 1. And the B matrix would be 0t. So this is a simple representation, approximate, in an approximate manner of a second order system. And we can compute the controllability matrix and its inverse, and we get something like this: 1t, 0, 1 for the A matrix, and the B matrix would be 0t. So the controllability matrix is the matrix A and B, and when you do that, you can obtain, I don't know if this is correct. Yeah, I'm sorry, probably making a mistake there. Let's see. Let's see. You have, okay, A is your matrix 1, 0, and then 0, 1, and that's the A matrix. Oh no, 0t, 1t, and the B matrix is 0t. So the Kalman controllability matrix is, well, 0t, that's B, and AB. AB is just t squared here and t here. So yeah, so there is a mistake there. So this is your Kalman controllability matrix, and you invert this matrix. You can pull out t as a common factor, and you will have 0t, 1, 1. All right? So that's B and A times B. Okay. So this matrix is invertible because the determinant is just minus t, and therefore the inverse of the Kalman controllability matrix will be K inverse will be 1 over t here, and minus 1 over t of the determinant. You'll have 1 minus 1 over t squared. And then you will have the inverse of that, which is 1, 0, minus t minus 1. So the last row of the inverse of the controllability matrix gives you minus 1 and 0. So x1 should be your flat output. It doesn't matter that it has these factors, because remember, the flat output is proportional to the last row of the inverse of the controllability matrix multiplied by x, by the state. So we can take this proportionality factor so that we can kill any coefficients and make it more comfortable. So the last row of the inverse of the controllability matrix is proportional to x1, and therefore we can take the flat output to be x1. We don't need to take plus 1 over t squared x1. There's no need for that. So this is the flat output, and x2, x1 of k plus 1 will be fk plus 1, and x2 that can be solved from here is the difference between these two divided by t. So the difference of those two divided by t when x1 is the flat output is fk plus 1 minus fk arising from this difference divided by t. So x2 is parameterized by the flat output and one advance. And u would require a second advance of x1, a first advance of x2, a forward shift of x2 or two forward shift of x1. So a forward shift of x2 is fk plus 2 minus fk plus 1, and then you add x2, which is this, you get minus 2fk, and you get plus fk here with the minus of x2. So the input-output representation is given by this. And it's clear that the flat output is this, the forward shift of the flat output is the second state, and the control is related to the flat output in this apparently non-causal manner. So that's for the Euler discretization. Very nice. The Euler discretization has a property that, let's say, the relative degree of the flat output coincides with the order of the system. So you need two time shift of the flat output to get the control. So the relative degree is 2. And you can parameterize everything now. Now we do an exact discretization. The exact discretization of this second order system entitles the variation of constant formula. If you have a system like this, the value of x at time t1 can be computed as a t1 minus, let's say, t0 times x at time t0 plus the integral from t0 to t1 of e to the a t0 to t in general, t minus tau b u of tau d tau. Now, if you make a piecewise constant control input so that between sampling times you have a constant value of u and it changes for the next period of sampling, you can use this formula to obtain an exact value of the state at time k plus 1 as related to the state at time k by making u constant and making t1 equals tk plus 1 and t0 equals tk, and therefore you establish a relation between x of tk plus 1, which is exact, under the assumption that the control is piecewise constant. So the next value of the state is e to the a tk plus 1 minus tk. That we can say that this is a sampling time. Is a difference between the next sample and the actual sample, and that could be equals to capital T. And then, because u is constant, you can pull it out. So you have t from tk to tk plus 1 of e to the a t should be substituted by tk plus 1 minus tk minus tau times b. And this multiplies by the constant value of u. If you do this exact discretization, you will have an FG representation of your continuous time system, and therefore you have a more accurate description of the evolution of the system. If you do that, then the natural states of the system will be represented here as x1, x2. But notice that UK now influences both x1 and x2. It's different as before. U was affecting only the second state, but here it affects both states. So the structure of the system has changed completely in this state space representation. So now you compute the controllability matrix. It turns out to be something like this, and the inverse of the controllability matrix. And now you have that the flat output, which is related or proportional to the last row of the inverse of the controllability matrix times the state, can be simplified, eliminating some common factor or some constant, which is common factor to this linear combination, is just this type of relation. So the flat output involves the two states of the system. Before, we had the flat output related to only the first state of the system. So the flat output completely changes the nature when you do an exact discretization or when you do an approximate discretization. And the relative degree of the flat output in general doesn't hold, because when you do it from here, you will the relative degree will not in general hold, but this would be your linear combination of the states to get the flat output. So the parametrization of all the states is different now, and the control U depends on the flat output and a finite number of shifts of the flat output all the way up to second order. X2 represents this difference, and X1 represents this forward difference. So the structural properties of the exactly discretized system are different from those of the corresponding approximate discretized models. So it's a matter of taste. Flatness equally applies to both of them. But do you want to use an exact discretization or do you want to use an approximate discretization? Be aware of the fact that they have basically different structures, and the flat output has a different definition than in the approximate state. And it involves the two states. So that means that you have to be able to measure both states. In the previous case, you only measured one state, which was the first state, and that makes a difference in the design. Any question?
I missed the exact.
Pardon?
Exactly discretized system, not the delay model.
This is an exact discretization, as I explained here.
Oh, okay.
This type of discretization. It's called the exact discretization, assuming that the control is piecewise constant.
As opposed to Euler.
Yeah, as opposed to Euler that only approximates the derivatives. So the dynamics is quite different. As you can see from here, the control input enters both channels. And
this is very useful when the sampling period is not very small.
Yeah, if the sampling period is very small, then the flat output tends to be the first. This minus wouldn't make any difference. The flat output would be the first state. If let's say t is so small that you can neglect this, the flat output coincides with the other. So the approximation, the exact approximation leads in a limit to the same original differential equations, but only when t goes to 0. So yeah, and this presence of u, the flat output is such that you're trying to eliminate the influence of u in the first time shift of the flat output. You see, the next flat output contains x1 and x2. And here you're subtracting this portion from the multiplication by t halves of the input. So they will coincide and have different sign because x1 was put to be negative. When you do that, you eliminate the control input from the definition of the flat output. So the next value of f will not have the presence of u. So the second time shift will recently exhibit the influence of u. And this is where you have a second order. So we have an application here of a very well-known model. It's the model of Samuels. This is a simplified model of Samuelson, in which you have the economic variables naturally described at instants of time which are varying, let's say, from month to month or year to year, or presidential period to presidential period. you're free to choose your time scale. So in this model, you have this definition of the national income. The national income is the sum of the consumption plus the investment plus the government expenditure. So you have these three variables conforming the national income. And one of the assumptions of Samuelson was that the consumption is proportional to the previous value of the national income. So if your national income in the previous year was this given amount, that will determine somehow the consumption for the next year. People or the government will consume according to the most recent experience of the behavior of the national income. And the investment is sort of a difference of the consumption, or let's say the rate of consumption from one year to the next. So the previous year to the one you have, sort of the difference multiplied by a certain factor beta. This factor beta is called the acceleration factor, and this factor alpha is called the multiplicative factor. So the economy somehow depends via this multiplicative factor in affecting the national income of last year to sort of reflect what the consumption of this year is going to be. And the investment is basically watching for the fluctuations of the consumption. If the consumption increased from last year to the new year, then the investment is proportional to that increase in consumption. If on the contrary, the consumption decreases, the investment will also be affected in that proportional manner. So there is a very simple way then to obtain, thanks to this relation, substitute C in terms of xk minus 1, I in terms of this difference, which in turn can be placed in terms of the difference of alpha xk minus 1 and alpha xk minus 2, and the government expenditure acts as a control variable. This is what the government has in its power. So xk gives you this relation with the previous value of x, and then you involve the investment in this equation, and you get this relation, and you have the government expenditure. So you have a dynamical system which is very well known for computing the national income in terms of the previous values of the national income and the government expenditure. And that autoregressive model can be put in terms of a state space representation by defining x1 as xk minus 2 and x2 as a forward time shift of x1, which is xk minus 1. So the state space representation is very well known, it's like that, and u will still be the value of the control taken in the present year. So everything is causal, but now you see that the flat output here is the national income. Is the evolution of the national income which will determine the evolution of everything in the economy. So the controllability matrix will be 0, 1, and then A times, this is the matrix B, or the vector B, and then A times B is 1 alpha 1 plus beta. So the inverse of the controllability matrix, this controllability matrix has determinant minus 1. The inverse of this will be something like that. And you multiply by minus 1, and you change the sign of all these things inside the matrix. So the last row of the controllability matrix tells you that the flat output will be x1. So the last row multiplied by this state will give you x1. So the flat output is the national income. And you can planify things because the national income will be able to parameterize all the state variables. x1 is just f, x2 is the forward value of x1, so that's fk plus 1, and the control input u was seen to satisfy this relation with the flat output. So you have a difference parameterization of all the state variables, and if you want to plan for the national income in the next 5 years, these are the relations you should use, and this will give you the necessary government expenditure in the next 5 years. In that planning horizon, that will give you the control input. So the system essentially is something like that. It's just a pure delay system. If you redefine your control input to be a new control input V, which eliminates, in this definition, eliminating the influence of this term and this term, you will have that V, the new control input, is related by means of two forward advances to the flat output. Two backwards delays will give you the input. So the input will affect the flat output in 2 time steps. But this is just the say, let's call it Brunowski canonical form of the flat output. So it's a pure time shift system, the same as we had in the continuous time as pure integration systems. Here you have pure forward time shifts. Forward time shift are analogous to integrations. Backwards time shift, forward time shift are analogous to differentiation. Backwards time shift are analogous to integration. So, and we can make that relation precise. So, if you want to planify the trajectory for the flat output, offline you will have fk plus 1 and fk plus 2. Those are the nominal values, and the trajectory tracking will be solved by feeding back the tracking error and the forward tracking error and the precompensation in V. Therefore, the control, the nominal control can be computed, and you will have the control law in terms of this transform variable. It's very easy to transform this back again into the VK formulation, into the UK formulation. So UK will have a different expression, and you have this is your control in terms of the states, or in terms of the tracking errors in the present and in the future. So by using this feeding back of the tracking errors, you will obtain a tracking error dynamics in which the coefficients K2 and K1 used here will give you stability of the system and convergence towards a steady state. This is another example which is also nice to have around in order to explore the implications of flatness in a concrete physical problem, in which you have a heating system, just warming a slab of material, and you have a discrete points in the space. You are measuring the temperature at these 3 points, and the objective is to try to control the temperature of this point from this control input. So the basic physical law to be used here is called Newton's law of cooling. Newton also produced some work in the area of heating and cooling systems, and in his law of his physical law of how the temperature propagates in a slab like that from one point to another has to do with the fact that the temperature in one point is sort of proportional to the sum of the temperature differences in the neighboring points. So, for instance, that gives you something like this: the difference of the temperature in the points B and C, plus the difference of the temperature between the points A and B, and some linear combination of those will give you the temperature in B. So the increase of temperature in B is proportional to the increase of temperature between A and B, and the increase the temperature difference between C and B, and A and B. So this is a very nice law, and and P is a parameter that depends on the conductivity properties of the material. So we assume that this is the case. So that's the model, and K here represents space. So I mean, K represents time, and A and B represents points. A, B, and C represents points in space, which are separated by a certain distance. If you look at that model, you will come to realize that you can write that model in state space form, and so the increase of temperature in C will be related to the somehow a linear relation between the temperature in C and B, and also the increase of temperature in B here is proportional to A, B, and C, and also A, which is closer to the heating element, you will have the direct temperature of the slab at the input. So there is a control system in which U triggers the dynamics traveling from the initial point to the final point of the slab, and the temperature evolves according to that dynamics. It's very nice linear dynamics. So if you have something like that, you have a discrete time system, and it would be nice to see if this system is flat. And by inspection, you can see that if you know C for all times, then if you know these two terms, you can compute B. If you know B, you know these two terms, you know C already, you can compute A. And now you know A, B, and C, you know A, B, and C that doesn't appear in this equation, now you can compute U. So the flat output is the temperature in the last slab. This is the flat output. That's the output that needs to be controlled, and it coincides with the flat output, and therefore is the one that you should try to relate to the input in a nice manner. So the state space model has this structure. It's very reminiscent of the discretization of a partial differential equation with this typical matrix. I think it's called band matrix or Toeplitz matrix. So you have a dynamics which is very well known, and the controllability matrix can be computed to be something like this. So the inverse of the controllability matrix now has this structure. So the last row of the inverse of the controllability matrix tells you that because you have chosen this state, that the flat output is proportional to the first state. So that's the flat output. And you can obtain the difference parametrization or the observability matrix by taking the several forward time shift of the flat output up to the second order and related them to the state. You get this relation from the equations. So the next output, the next value of the flat output will be related to the control input. So this is the input-output dynamics in terms of the state. And you can do all sorts of things here, and because the inverse of this matrix will give you a parametrization of A, B, and C in terms of the flat output and the advances. Now you can compute C as the flat output, B as this relation, and A will be related to U. This is U. This A is the temperature. Well, no, this is a state. So, and U will be, you will obtain a third order model from U, which is quite complicated, something like this.